So I was gonna do.
Recording it.
Yes, yeah.
It did look
Is that recorded? Okay, great. Okay, welcome to Christian Lange's defense. Christian have a that ended up being longer than still gonna read it. Okay. Christian is 4 out of 9 kids from Utah. He went to Utah State for his undergraduate. We have a very special guest, which is his daughter in the back, Anna. He arrived in the summer of 2021. He and Emma started a new experiment in my lab. It was also a very new area for me, using chemical systems as photon emitters. And during his PhD, they really took us from being complete newbies to leaders in the field, in my opinion. So Christian is a high intensity individual. Watching him do research is kind of like watching someone run a marathon. He pushes himself often to exhaustion. He finds inspiration in discomfort. For example, if these are based on real examples, if you ask him what to do if you're maybe tired and unproductive, he'll say, just go into a cold room and keep trying to be productive. If you ask him, am I sleeping too much? He might say, well, we'll just sleep on the floor with a bag of sand. He pushes himself a lot, but that has really shown in his productivity. The project I gave him was a very difficult one. It was one that really had eluded the community of people who work with this system for 2 decades. It's integrating these molecular systems with high quality chip-based optics. There had been a lot of attempts at this. There had been some minor successes, but nothing that really obviously worked well. That meant Christian was set up for a very difficult PhD. And that also meant he was set up for a lot of failures. And that is the one thing that's one thing that I actually respect about him a lot. He failed a lot. He learned from it. He developed a lot of intuition about this system, and then he iterated through a huge amount. So what you're seeing here is kind of like what worked, but he went through so many different things that didn't work. Last year, I took him, we went to Europe and we visited a couple of groups who are the leaders of this field. And we were, I think, the first group kind of outside this small community of people that stems from one group to take on this project. And it was very fun to watch this guy from Utah come in and tell them a lot of things they didn't know about their system. So it was very satisfying. He's developed a massive amount of intuition about this system. I really do think he's one of the leaders in this field right now. And now I will say, I know it can be really hard to convey your PhD to your family, what you're actually doing. So I was going to do it in a couple sentences, although I think you might have it in the introduction as well. But at the smallest scale, particles are very different. Light consists of particles called photons. It is a world full of uncertainty. The particles can exist in multiple states at the same time. But this coexistence, which we call superposition, has enormous potential. And it can take us way beyond what we currently can do in computation and measurement. But it is extremely hard, and it really does require perfection, because anything that can take information away from your system will, and destroy this superposition, this uncertainty. So Christian's project has been to use single molecules to emit nearly perfect photons. And it has been to do it on a integrated photonic chip that we could eventually scale and really develop for some applications. So with that, I will let Christian start, and let's welcome Christian. And please feel free to get food. Oh, I was also going to say, if you haven't been to a defense, the way it works is that he will give his presentation, and then you guys can ask questions, and then the committee is going to grill him for a little bit by yourselves, and then then we will decide.
Okay, great. All right. Well, thank you all for coming. Thank you, John, for the fine introduction, and thanks especially to the committee for the time you devote to this as well. So, my PhD has been focused on, as John said, a molecule and its interaction with light. And I've done essentially three things over the last 4.5 years. First, as a first-generation grad student on this project, I helped to build the experiment and to characterize the way the molecule interacted with light. Second, I made collective systems of these molecules to couple them in free space and to study how they interact with each other through light. And then over the last couple of years, I used a nanophotonic circuit to enhance the interaction of these molecules with light, to engineer that. And so I'd like to start by briefly motivating why we would be interested in this field of quantum optics. So when people talk about quantum technology, they talk about it in terms of the so-called first quantum revolution and second quantum revolution. The first quantum revolution is gave birth to the technologies of the semiconductor, transistor, the MRI, GPS, and of course, the internet, or lasers specifically, which is a requirement for the internet as we see it today. And all of these technologies require an understanding of quantum mechanics, but none of them require an exquisite control of a single quantum state. And so the prediction is that the second quantum revolution is going to take the control over individual quantum states that we've developed over the past 2 decades and kind of radicalize a lot of technological fields. Instead of having the internet based on lasers, if you use quantum light, you can have an internet which is in principle arbitrarily secure. Of course, there's the holy grail of quantum technology, which is a computer that uses the complexity of quantum states to achieve a very high computational advantage for certain types of problems. And then, of course, quantum sensing, which uses the sensitivity of quantum states to break the current limits in metrology and sensing. So in the subset of quantum technologies which rely on photons, like particles of light, there have been a number of advances over the past 2 decades which make right now a very exciting time for photonic quantum technologies. On the theoretical side, as an example, there are protocols for doing quantum computing with photons, which involve taking photons which are not entangled, sacrificing some of them to build up a large entangled state, and then adaptively measuring the entangled state and then modifying it to do a computation in a way that is much more forgiving of photon loss than other protocols have been. On the hardware side, in my opinion, one of the biggest enablers for photonic quantum technology, which really started to be commercialized in the 2010s, was the ability to detect photons with very high levels of efficiency. And so where we are right now is we can detect a photon with above 99% efficiency. And even more recently, we've developed the ability to distinguish between a single photon and 2 photons and 3 photons in a single optical mode. So we've gotten to the point where we have useful protocols, and we're really good at manipulating and detecting photons. But the last frontier is really being able to generate quantum light in a way that we want and on demand. Current methods of generating quantum light are probabilistic and are really not scalable. And the reason that we are interested in this molecule, the molecule that I work on, is because it has a lot of promise for being able to generate useful types of quantum light or technologies. Okay, so this is that molecule. Its name is dibenzotyrrolene. It's made out of benzene rings. You can dope it into a lot of different structures. What we do is we dope this molecule into a crystal anthracene. This is what anthracene looks like. The doping concentrations are as high as 1 part per million, but it can be as low as a part in a billion or less, depending on how you synthesize it. This is what the level structure of the molecule looks like. And so if you have an electron, it's in the ground state, and you send a laser and you drive the electron to the excited state, and then it decays back down. And it can decay down 2 paths. Either it decays right down to the ground state and emits a useful photon, that's what's in red, or it will decay down to a vibrational manifold, and these photons are non-usable for reasons I can explain later. And the ratio is about 30% to this and then 70% to that. Okay, so you can use time dynamics to understand the system. If you measure the lifetime of the system, so this is what you do is you send in a laser light for a long time to drive it to steady state, and then you switch off the laser light very quickly in about 800 picoseconds, and then the state will decay, and you can just fit an exponential decay to that, and you'll get either 4 nanoseconds or 5 nanoseconds, depending on how the molecule inserts itself into the lattice. This is called an autocorrelation spectrum. The way this works is you are collecting photons from the molecule, and when you collect the first photon, that's when the experiment starts, and you ask the question of how long does it take to collect the next photon, and what is the probability of collecting another photon in a certain amount of time. And this spectrum is a way of measuring the population of the excited state after a photon detection event. So you can think about it this way: you detect a photon, which means you're in the ground state. And so the likelihood of detecting another photon is very close to zero. And then if you're continuing to drive with a laser, you slowly drive it higher to the excited state. And if it were very coherent, you would just drive the electron up, down, and you get sine wave. But because of interactions with the environment, that all damps out, and so it kind of damps out to an average. And so you can learn things about the coherence properties of the molecule by taking a spectrum.
So what's causing it not to go exactly to zero?
Yes, so this is probably background noise. We think that, so when we're measuring photons, we're actually measuring these yellow photons. So we drive with a resonant laser light, and we filter out only this light. And so ordinarily, most of your noise would be from your laser light, but because you have very good filters, the laser light is probably not the background. The background is probably from nearby molecules, because this is relatively high density. And so if you're driving resonant to one molecule, even though you're off resonant to other molecules, you're going to excite them a little bit. And their phonon sidebands are, a few nanometers broad. And so if you sum up all the phonon sidebands from a bunch of different molecules, that'll add up to a little bit of background. And then there's also contribution to the background from your the dark counts of your photon detector. So those we think are the main contributors.
So how much so I would imagine that second yellow photon, that's the little bitty one.
This guy.
Yeah, that's slow. So
sorry,
does that affect this process, because you have to get back to the ground state, right?
Yeah, so this is my mistake. I should have clarified. It was a bad idea for me to draw this the same as this. So this is an optical transition photon, but then the vibrational levels relax down here with the release of a phonon.
Okay.
So that vibration goes off, and these last about a picosecond.
Okay, so that's even faster.
Yeah, so this doesn't introduce any optical noise, and it's pretty much instantaneous with respect to the 4 nanosecond decay time.
Okay.
Okay,
Good worse.
Okay, so what is special about this molecule is its level of interaction with this environment, is one way to say it. So, and you can understand this as follows. So if you take a laser with a certain frequency and you scan it over this transition, when you're resonant to the transition, then you'll be driving photons like crazy. And so this is a peak you would get as you scan the laser over the transition. And the width of this peak, if you have a very weak excitation laser light, is a measure of all the decoherence in your system. So you have gamma 1, which is equal to the rate at which you decay, plus an extra pure dephasing term. The pure dephasing term just means that there is stuff in the environment which is jittering your molecule, jittering this energy level. That's one way to understand it. It's not perfectly precise, but I can maybe go into that more detail later. But all that does is it broadens this transition. And what's special about this molecule is if you cool it down to 2 Kelvin, that component goes away. And the width of the transition becomes we call lifetime limited. It's limited only by the decay time. And what that means is that the molecule, as far as the molecule is concerned, the interaction with the environment is frozen out. It's like it's just sitting in free space. And if you drive this transition many times, the photons will be identical to each other. And right now, as of just 2 days ago, this molecule holds the world record for indistinguishable photons from an optical emitter, because they took 2 separate organic molecules on a chip and interfered the photons and found that they were 97% indistinguishable, which is very high for a solid state emitter.
What was the previous record?
The previous record was 93% from 2 separate epitaxial quantum dots. That was just a couple of years ago. For indistinguishable photons from a single photon emitter, epitaxial quantum dots still hold the record. It's like 99%, but from 2 separate emitters, DBT now holds the record.
I know you're going to address this later, but how much of that is just due to a difference in energy or transition frequency for the two?
How much of the
the problem that you
well, they have 3% of
yeah.
distinguishability. It is presumed for DBT, most of the distinguishability is due to its pure dephasing component.
Oh, it's from the dephasing.
That's what people think, because
so if they'd gotten it colder, it would have been even less.
In principle, I mean, I guess there's also probably some like slow drift, which means if you integrate the HOM over a long period of time, like the slow drift back and forth will affect things. So I guess I can't say with confidence what component is due to this and what component is due to like electronic noise. So,
Okay.
but the nice thing is that it is just an electronic transition. There's no spin in the story, and so any like nuclear spin bath effects are not a contributor. Okay. Great. Okay, so one downside of this being a solid state emitter as opposed to like a trapped atom is that every molecule is in a slightly different environment, and so they all feel a different strain, feel a different electric field, and so they all have different resonant frequencies. So this is one crystal, and each of these lines represents a molecule, and they all have different resonant frequency. And so in order to do anything useful with separate molecules, you need to tune them into resonance so that their photons are mutually indistinguishable from each other. One cool thing about these molecules is that they have a built-in tuning mechanism. If you shine intense laser light on a crystal of DBT and anthracene, what you'll find is that the resonant frequencies will tune permanently. So if you pump with strong laser light, it moves up here, turn off the laser light, and the resonant frequency will still be changed, and that will stay steady for months without regressing. The mechanism for this is thought to be like an ionization process, where if you put very strong laser light onto DBT, an electron will get ejected out into the surrounding lattice, and then DBT will steal an electron from the lattice. And now you have a whole electron pair with an electric field between them, which shifts the molecule. And for whatever reason, this whole electron pair has a very long recombination time, probably because anthracene is a wide bandgap semiconductor. So when they travel around and get trapped in defect states, they stay for a long time, and it's not easy to, or maybe they get stuck on the like the boundaries of the crystal. It's not entirely clear. But this is useful because now you can take molecules and shift them into resonance with each other. And then the molecules are all speaking on the same wavelength, and in principle, you can do useful things. And that this is, it's steady. It'll stay in resonance for a long time. Okay, so after characterizing the molecule, I spent about a year or two working on just trying to understand collective interactions of them in free space. So the way to understand this, I'll just give some intuition for collective interactions. If you take two dipoles and bring them very close together, they will couple to form two different eigenmodes, a symmetric one where they oscillate in phase, and an anti-symmetric one where they oscillate out of phase. This is essentially the same thing as a tuning fork. If you hit a tuning fork against a table, you excite a lot of modes initially, among them being one which like this, one which like this. And the in-phase one radiates power away faster because of a constructor interference. Each time is sending out a wave, and the two waves interfere and send away power. And so this is very loud, but it damps away very quickly. And then all that's left is the anti-symmetric one, and that's what you actually hear when you strike a tuning fork. And it's a very similar story in the quantum picture. If you take two molecules and you couple them, they'll form a symmetric superposition, which decays rapidly, and then an anti-symmetric one, which has suppressed decay. It holds onto that energy for a long time. Under certain circumstances, another interesting thing is if two molecules are coupled, you can actually drive a two-photon transition, where you can absorb two correlated photons and doubly excite both molecules, at which point they cascade down this ladder and emit two photons, which now have some of those correlations or time and energy correlated. And this is interesting because if you go to the limit of many emitters coupled together, you excite them all, like you invert the system, and then it cascades down and releases a bunch of photons, which have time and energy correlations. This entangled light is in principle useful for metrology. So just to give you an idea of this, if you have a laser and you're trying to measure a phase difference, you're limited by what's called the standard quantum limit. It's your phase sensitivity goes as 1 over square root of n, where n is the number of photons that you do the measurement with. Whereas if you were to do the same measurement with these, the phase sensitivity would go as 1 over n. So what this means is that if you had 100 photons in an interferometric measurement with the laser, you'd get a sensitivity of like 1 part in 10. Your phase uncertainty would be 1 part in 10, whereas with this light, it would be like 1 part in 1 over 100. So much lower uncertainty. Yes, please.
I have a question. So can you just go to two previous slides when you were just showing like a singlet and triplet? So then are you saying that the one which is kind of the symmetric superposition, you call it superradiance?
Yes, that's the term that I've been using.
So
there's sure. So sometimes when people say superradiance, they mean like a superradiant burst. Is that your?
No, my question is that for like at least like for the two case, for the two atom case, I think to me, it doesn't make sense to talk about super radiance. Do you agree? Because I mean, we have to have like that super, the super radiance is just a super extensive scaling. So then for two, then you get like twice the time of individual, twice the rate of the individual one. So and n squared is also the same, right? So then I think two is kind of like a
So there, yeah,
not fair. So yeah, I just want to understand that your terminology, just because you're using also the DQ ladder. So you don't necessarily mean that that symmetric state is your super radiant state.
so in the examples when they've coupled two like pairs of quantum emitters to make this enhanced decay, they've done it in quantum dots, they've done it a few times with molecules. All I'm saying is in each case, in each instance of those, the literature refers to it as a super radiant state, even if it is just a single excitation manifold. And so I've been kind of sharing that terminology. This is like Peter Lodel, he referred to it in that way. But then there's also the Dickey ladder. So, and it is true, like you're never gonna get a super radiant burst from a single photon, obviously. So,
Or even if you have like two atoms, then I think it doesn't make sense to talk about super radiance,
Sure.
right? Another one, when you were just talking about your Dickey ladder, can you go to the
Sure.
next one? So no, maybe the one that you had like more photons.
Sure.
So if I interpret it correctly, so each arrow corresponds to different m number, right? So is that what you meant by each photon? So
Yeah, so
you're just kind of changing your m, yeah. Correct. So are you implying that the photons that is kind of like interesting for you is coming from the very last transition?
No, for the metrological purpose, you need all the photons that come from this burst. I think you'd had it's a whole, it's not quite a Fock state, but it's close to a Fock state. And then you had another burst of that, and then you were doing interferometric measurement of them. The quantum fissure just scales very close to the Heisenberg limit.
No, that I understand. I just wanted to schematically understand that when you have these kind of, or maybe that's just a picture, but then the yellow photons, the yellow photons that you say, it seems that as if you're saying that these are like the ones that they are interesting, but I think that they should actually be boring, aren't they? Because when you get the unison emission from the emitter, do you remember which transition? Actually, when you get to the middle of the ladder, that's where you have the interesting photon.
All I'm saying, so this paper, I forgot the reference here, Polish and Sirac, they just said that if you have, if I understand the paper right, and it could be that I'm misunderstanding it, but if you have like an n size Dickey state that's inside like a 1D waveguide, right, and then you just get that burst out, and then you interfere those, that's the scaling.
So you fully invert the system
Yeah.
and you get all those photons out.
If I remember the paper correctly, he did mention it's true. Like the reason why the quantum information scales the way it does is because of the stuff in the middle.
Yeah.
But the fact of the matter is, if you get the burst, that's the scaling.
Yeah, because before and after, I think that your photons are not correlated. Yeah. So there's nothing interesting at the beginning when you start the avalanche process, and then later
Yes,
when you kind of go to
that's
the
correct.
ground state, it's actually in the middle of the ladder, which is
Yes. Yeah. Although I don't actually know the answer to this. If you lose these tail end photons, I presume it would be more robust to photon loss than if you're to lose one of the ones in the middle, but I actually don't know the answer to that.
Super interesting question. I haven't heard people talk about preparing maybe a state in the middle,
Yeah.
rather than just going. I guess Alex, you could answer that question as well with your system. It's always like invert the whole thing.
Yeah.
Could you like continuously drive to something and then get?
But it's kind of, because I guess the convenience of inverting it is like this is a fully symmetric state, and you need to go to a fully symmetric state to access these fully symmetric ones. It's not so obvious how do you go to the state where you have 3 excitations, but it's also fully symmetric. It's, I'm sure, experimentally much more difficult.
no, but I think that like Francis' paper, I think that you had like a general condition for that gamma dot to be kind of like positive for arbitrary initial states, so you can check.
Okay, great. So we set out to look for pairs of emitters in a crystal. They were interacting. The way we did this is we first made nanocrystals of anthracene. They were doped with a lot of DBT. So on the order of like 1,000 molecules of DBT per cubic micron, which is pretty close to that 1 part per million.
Oh, I have a question.
Please.
I'm sure you said it. What are the wavelengths here?
It's rubidium, 780. It's very close to rubidium.
So the photons that are coming from your molecule are 780.
Yeah, so and these ones are 74, 74.4.
They're
but-
right there.
Yeah,
Never mind.
yeah. So it actually is an interesting point because depending on how you synthesize the crystal, the molecules have different wavelengths. We synthesize them two different ways, either centered around like 784 or centered around 780, which is useful because there's rubidium. But people using the same molecules, DPT and anthracene, with different insertion sites have made them as blue as 720. So there's a lot there in terms of the chemistry, which is not totally understood. Anyway, so the way we set out to look for pairs of molecules that are interacting is we would scan over a region of these resonances and increase the laser power and see if we could see a 2-photon transition. That's what we were looking for. Initially, we didn't see anything. We looked for a couple of months, and then we found that if we first did this thing where you pump them with a lot of laser light, shift everything around, let it settle, let the electromagnetic fields inside the crystal do what they're going to do. Then we looked again, and in about half the crystals, we were able to find a signature of interaction. And this is what that looks like. So here's one molecular resonance, and here's another molecular resonance. And as you increase the laser power here, you see a sharp peak in the center, which indicates the 2-photon transition where you're doubly exciting the system. And then if you want to be absolutely certain that this is a 2-photon transition, you can take the autocorrelation and you find that there's a bunching near the center, which just means after you collect a photon, you're more likely to collect another photon in a short time window. And if you'll remember the autocorrelation spectra I showed earlier, typically this dips down to 0. So the fact that this is now a super bunch with like an exponential arm there indicates that the photons are correlated and that we're actually looking at two coupled molecules.
Is there any information in like the widths of these things?
In principle, I have not fit that.
Okay, because like the one on the right looks widest, the one on the left looks left.
He means that he means
Oh, it's
Yeah.
no, there's no fit here, but yes, there's a lot of information. In fact, this saturation measurement, if I'm not mistaken, contains all the information. If you combine this with a lifetime of one of the molecules, let's say the far detuned limit, you can collect. Then you have the lifetime. You have the branching ratio of useful photons versus not useful photons, alpha. You have the coupling strength J, and you also have the pure phasing gamma star. So this is the superradiant and this is the subradiant one, if you'll allow that terminology. Yeah. Yeah. And then I'll show some more characterization of these molecules later.
So in this case,
Please.
what's the detuning between the two and the coupling?
What's the detuning?
Yeah.
So the detuning looks to be like 3 gigahertz, and the coupling strength is 1 gigahertz. So if the
Okay.
molecules were resonant, then there would be a splitting of 2 gigahertz. So it'd be like come to resonance here, and that's what the intercept cross would be.
And this is basically one slice of data you could take while changing the
Yeah.
detuning.
Yes. Yeah,
Okay.
that's right. Okay, so we took pairs of interacting molecules. We had 10 of these, and we just tried to do this probabilistic thing, just dump laser light on it and see if we could coax them into resonance. And in 2 cases, we were able to coax them into resonance. And so here you can see so as you bring them into resonance, they form those symmetric and anti-symmetric states. And the limit that the molecules are perfectly resonant with each other, they're talking with the same frequency of photons, then that's when you have the perfectly symmetric and anti-symmetric states. And you can see the anti-symmetric state getting shorter and shorter until it disappears. The reason for that is that you're exciting your molecules with a laser light, which is, electric field up, down, up, down. It's symmetric, whereas your molecule eigenstate is anti-symmetric. And so in the limit that is perfectly anti-symmetric, your laser light can no longer talk to it, and so it goes dark. And the point at which it goes dark, the anti-crossing, you can just fit a line to this curve, and that will tell you what the coupling strength J is between the molecules. In this case, it's like 120 megahertz or something, which is like a factor of 3 of the decay rate gamma. Okay, and then you can characterize the superradiant and subradiant states spectrally, so you can measure the lifetimes and show that superradiant state is a little bit enhanced over the subradiant state. These were not brought perfectly into resonance. This is almost resonant so that you can actually still access the subradiant state. And then if you do an autocorrelation, you find that the superradiant state has faster Rabi oscillations, just indicating that this is enhanced interaction with the laser light. This is an enhanced interaction with just decaying into the vacuum.
Do you change the amount that goes directly back versus going through those vibrationally excited states?
Oh yeah, yes. So that is the yeah, your alpha Frank-Condon factor is enhanced by this interaction. In principle, it doesn't really matter on J, as long as they're in resonance. I think that your alpha factor should just be the so your decay rate is just going to be 2 let's say gamma ZPL plus whatever vibrational decay you had earlier.
Mhm.
So the vibrational decay is not enhanced,
Mhm.
but this decay is enhanced. So and this decay can be doubled in the limit that they're interacting, which is also why there isn't a huge enhancement here. Is this because when we fitted everything out, we found that for these molecules, this branching ratio is about 10%. And so if you go from, this, let's say 1 part in 10 to 2 parts in 10, plus the rest of the decay, this doesn't give you a huge enhancement.
So why doesn't the blue get enhanced?
It's a bit of a nuanced argument. Essentially, okay, so we know that the decay from the vibrational states to the ground state is a
That we know.
phonon interaction. So that
Yeah.
the point is there shouldn't be, we assume that there isn't any superradiant phonon decay or subradiant phonon decay.
Yeah.
You could argue with that, but that's kind of the assumption that we have.
So it's the vibrational decay part labels which one actually decayed, and so you don't get interference. Is that the argument you're making?
The argument that I would take is that so when the super or this enhanced decay is all about coupling, let's say, like a symmetric state to a symmetric state versus anti-symmetric to symmetric has no enhancement, et cetera. And so the point is for any symmetry, right, this plus this or this minus this, there's going to be that same symmetry in this manifold. You can write the eigenstates however you like. And since the trace of the gamma matrix is always going to be the same.
I see it.
Yeah. Okay.
Okay.
Good. Okay. I'm glad. That was my idea. I've argued it a few times. I've never read it anywhere, so I have 90% confidence in it, but that's okay. Now, obviously, our end goal is to have a many body state, and we were able to bring 3 molecules into resonance in 1 nanocritical using this. But the fact of the matter is this is probably not going to be scalable to 10 or 20 molecules, which means that the route forward for making collective systems is going to be using a nanophotonic device to enhance interactions between molecules to build up a large collective state, which brings me to the last couple of years of my PhD. Okay, so the idea of cavity QED is if you take a quantum emitter and you put it inside a nanophotonic cavity, you can enhance its interaction with light. And the intuition for that is as follows. You have 2 mirrors here, and you have a photon in the cavity, which is resonant to this cavity. That means it'll go back and forth many times before decaying out with kappa, which means it'll pass through your molecule many times, which means the likelihood that it'll be absorbed by the molecule is greater than if it's in free space. And because all fundamental interactions work the same forward in time versus backwards in time, and this is just the Hermitian conjugate part of the Hamiltonian, that means if you have an excitation of the molecule, if it's more likely to absorb a photon that's in the cavity, resonant to the cavity, then it's also more likely to emit a photon resonant to the cavity into the cavity. And so the whole point of this is that if you make a cavity which is resonant to a certain transition, you can enhance that transition, which is useful for 2 reasons. First of all, as I said, when it emits a photon, it's encouraged to emit a photon into the cavity, whereas a naked molecule would send photons everywhere into free space. If you have a very strong enhancement, then you can actually make it where a molecule almost always emits a photon into a cavity. And then if your cavity is coupled to a useful mode, like an optical fiber or something, then essentially every time your your molecule emits a photon, it will decay it into an optical fiber or something, and you can go and actually do useful things with those photons. The second reason it's useful is that, as I mentioned before, there's always going to be some pure dephasing in your system, even a little bit. And so you could kind of imagine that as like this level jittering or broadening. But if you enhance the decay rate, you can, this is an imprecise way of saying it, but you can kind of outrun the dephasing. As if your decay rate is large compared to this dephasing, then the photons it emits will be more indistinguishable. That's true in the case of pure dephasing. That's not true in the case of spectral wandering, but that's how it goes.
So you just are saying per cell.
Per cell.
Okay.
This is for
Okay. Yes.
my mom's on the call. Come on.
I just
Yes, Purcell enhancement. That's it. Okay, Ed Purcell was a professor at Purdue. The rest of you. Okay. And of course, the dream of this is if you can have a very strong light matter interaction and then also have a very scalable, then you could make a system where you have like deterministic emission of identical photons into all these modes, and then you can go and do scalable quantum technologies with that. That's the dream. Okay, so this is a fraction of the collage of all the failed ways of doing this. I won't go into depth into all these ways, but they're basically two strategies. So the difficult thing is that you're trying to get a molecule close to this nanophotonic cavity without degrading the molecule and without ruining your beautiful cavity mode that you worked all that time in the clean room to make. And there are basically two strategies to do this. You can either put the molecule into a crystal, which is super small enough that it doesn't disrupt the cavity mode. But then you risk squeezing the molecule, right? Putting it near an interface, and there'll be dephasing from that. Or you can make the crystal so large that it doesn't bother the cavity mode, because as far as the cavity mode is concerned, it's like a bulk. And we actually found that last strategy was the one that worked. Okay, so this is our integration strategy. So we have this, we call this the octopus. It's just an array of nanophotonic cavities. If you zoom in on one of these, this is what it looks like. It's a nanobeam cavity. So this is a ridge of silicon nitride. The light travels in here. And the way you can think about this is if you poke a bunch of holes in a nanobeam cavity, the way, the constructive interference from the light that scatters off of each of these means that this forms a mirror. It's just a Bragg mirror, essentially. And so a photon leaks through this mirror. There's a mirror over here. The photon will just bounce back and forth about 1,000 times before leaking out. And so if you put a molecule very close to the cavity, then your interaction of light is going to be greatly enhanced.
So the distance between holes are changing? That's how you're kind of...
The tapering is actually not the distance of holes, it's the size of the hole. So
okay.
The standard strategy, like the Mark Longcar pioneered, is just to modify the distance. But there's this paper that if you just modify the size of the holes and then you make it linear, then you get a Gaussian envelope, which is very lossy, or not lossy, excuse me. Great. Okay, so then we take our crystal of anthracene doped with dibenzotyrrolene and stamp it on top of all of these. This is kind of what it would look like in a cross section. You have the cavity mode, substrate. This is just air in the gray areas. This is your crystal, and then you have to coat it with a layer of polyvinyl alcohol to stabilize the crystal and keep it from evaporating. And because the cavity mode leaks into the anthracene, if there's a molecule there, then it will interact with that cavity mode. Kind of miraculously, the most common way that DBT inserts itself into the anthracene is oriented along this axis of the crystal, which also happens to be an O-axis of the birefringence. So anthracene is very birefringent, but as far as the molecule is concerned, because it's oriented along the O-axis, there's no birefringence at all. It's just bulk medium as far as the molecule is concerned, which is very fortuitous. Okay, so we have these grading couplers on either side. This just takes a laser light and focuses it into the wire, so you can interact with the cavity, and then measure it on this side. And then this is what a cavity looks like on resonance. As you tune the laser light until it is resonant with the cavity, on resonance, there's a burst of light indicating that the light's going back and forth many times. And if you look over here, you actually see transmitted light. So that means that on resonance, there's a lot of light here, and whatever leaks through goes out this way, and you can go and measure it. Okay, so the breakthrough which allowed this integration strategy to work was when we learned how to make these ultra high aspect ratio crystals. So these crystals are tens of micrometers wide, but only 200 nanometers thin or less. And the surface roughness is sub-nanometer, which means that you can stamp it onto a cavity mode without disrupting it a huge amount. And then what was remarkable is that when we learned how to do this, we also found that the inhomogeneous broadening of all the molecules decreased by about a factor of 10. So we now have a system here where there's high density of molecules. The inhomogeneous broadening is much less than it was before. And then it's kind of in the thin film regime where you can just couple it onto a nanophotonic structure. But this also kind of kindles the hope again of maybe if you were good enough at chemistry, you could decrease that inhomogeneous broadening a lot and then start to get interesting collective systems even without a cavity. But that's dream for now. I'll dwell a little bit, I don't want to spend too much time on this, but dwell a little bit on the synthesis method. So the battle you're always facing here is you want to form the crystal slowly so that it ends up being uniform and pretty and low surface roughness and all that. But if you form it too slowly, then it'll actually reject the DBT, and DBT won't be doped into it because DBT is a dopant, is an imperfection. And so if the crystalline lattice is too good, then it'll reject it. And this actually turns out to be, kind of tricky because, so this is the original way we grew it is, so it's in gas phase. Basically, you have a crucible here and you cover it with something. So that inside there, you have a saturated nitrogen atmosphere of anthracene and DBT molecules. then you take the lid off, and then the vapor quickly cools, and then these crystals form in these supersaturated vapor. It's the same way that snowflakes form. And then they just kind of float down, and then you can collect them on a substrate. But the problem with this is it's such a rapid cooling that you end up with all sorts of amorphous crap, and then it's not all useful for coupling. And so this is what we iterated towards. This is something I worked on this semester. The way that like really good chemists make nice crystals is always with a tube furnace. And the general strategies, you have like a heating stage here and a heating stage here. And you flow laminar gas down the center, and you have your chemical material here, so anthracene and DBT. It evaporates, and then when you flow gas, it pushes it into the cooling zone, which is a controlled temperature, and then the crystals form, and then you can deposit it. But the problem is that in order to get the right crystals, which are both pretty and also high density with DBT, the gradient between the cooling zones is quite large, and the gas flow has to be very, very slow. And so this is kind of a difficult combination of slow gas flow and also huge heating gradient. What the problem you run into is that if you have laminar flow is actually defined by the velocity of the gas going faster down the center than near the walls. And so you have low buoyancy, hot air here, going to cold air here, and the center reaches it first, which means now it's going to have a torque, and then you end up with convection currents at the interface between these two. And the convection currents are a huge problem because now your crystal is formed here, then it melts here, and then forms here, and then melts here. And as it does that, it's essentially zone refining itself. And every time it resolidifies, it pushes the DBT out. And the signature of this is if you see convection currents and then you look at what the molecules look like, you'll see a bunch of DBT right in the center and then nothing anywhere else, indicating that as have melted from the edges in and then solidifying over and over, it's just rejecting all that DBT. So what we ended up doing is we found that use like a plunger. Then instead of having laminar flow, you can do even better than laminar flow. You can just take a whole column of air and push it down uniformly. No convection currents or anything. Just move the column of saturated air, supersaturated, crystals grow, deposit onto your substrate. And then go to the races. Okay, so this is how you put a crystal onto a cavity.
How long does that,
Please?
how long does that process take of pushing the column of air? The squirrels is.
That's basically it. So you plug this hole, you have everything set, you wait for the temperature controllers to reach their set temperatures, stabilize, then you take your finger off and slide a test over, and then you close it. And that's it. And you can just see, you can see them form, and you can actually see with the naked eye, like if they're colorful, then you won, because that means you have thin film effects and all that. If it's just like white sparkles, then you've lost. You can try again. That's it. Spent a lot of my life doing that. Okay, so if you taper an optical fiber down, we just use by pulling an optical fiber very gently and then use a lighter to kind of melt it in the center, and then you can stretch it apart. And you can get, this is not super thin, but you can do that to make optical fibers down to like a micron thickness. And if you touch it to your crystal, it sticks to the crystal, you can pick it up, and then you can just stamp it on top of your cavity. And then you cool it down your cryostat, put a laser on the molecule, and when the molecule flashes, you see light coming out of the braided couplers. And that means the molecule is close to the cavity. Right, and so the way you probe the cavity interactions, you have an objective lens, and you send in a laser to this grading coupler, goes through the cavity, comes out the other grading coupler, and then you can measure it. The grading couplers are perpendicular to each other, so that the polarization of light which goes into here is different than this polarization, and you can just separate the input and output light using the different polarizations. So it just increases your signal to noise by a factor of 2. And this is what the signature looks like. So remember the flash of light when you're on resonance with the cavity. That's what this is. You're tuning your laser, and when you're resonant, you get a bright flash of light and a high transmission. But whenever you're resonant to the cavity and also to a molecule, there's a sharp dip. And this is where the molecule is working very hard to empty the cavity of photons. It's scattering light, reflecting light, all that kind of stuff. And the depth of this dip tells you how well that molecule is coupled to the cavity. Because if it dips down 50%, that means a molecule is scattering half of your laser light.
What coupling did you expect from simulation?
Much larger. We can go back. I'll address that in a second. Okay. So, yeah.
Okay, but I thought you said that when the molecule was coupled to the cavity, it would send the photons into the cavity.
It would send
the photons into the cavity.
So if you excite the molecule, it will deposit the photon into the cavity.
Uh-huh.
But if you excite the cavity in transmission, then the molecule will work to scatter that light and reflect it to keep the cavity empty. Unless I've grossly misunderstood the theory, but I mean you do see the transmission dips here. If you
Mhm.
excite the molecule, if the laser light were to go down here and excite the molecule there, then 50%, back the envelope, 50% of the molecule's light would go into the photonic circuit. Half would go here, half would go there. Whereas if you probe it in transmission, then you're actually exciting the cavity first rather than the molecule, and then it's you just get a different effect.
Okay,
Yeah.
I'll let it go.
Thank you.
Sorry, I just have a question. So the C that you are showing is like a cooperativity.
Yes.
That's the
Yeah, that's
for
cooperativity.
single molecule.
Yeah. Single molecule.
So you assume that there is just a single molecule,
Yes.
and then because I think that some maybe you kind of said later, but then it's just ensemble measurement that you right? So we have like a bunch of these molecules coupled to one of your cavities. Is that correct? Or the density is
Yes.
so low.
And so the density is high, but the transitions are very narrow.
Mhm.
And the transitions are very narrow compared to the inhomogeneous broadening. And so you can see one dip for every molecule.
But yeah, that's my question. How do you know that this is just one molecule?
Okay, well, if you did a great job, then you would do I think. Actually, it's not so obvious to me, because even if you took a G2, then let's say you have two molecules here in resonance. If you were to do a G2 of that, then that would still dip down to zero because you're probing.
No, actually, that's the point. So if you kind of keep increasing the number of molecules in your cavity, your G2 floor increases. So it's if your goal is kind of really have like a pure single photon, so then you really don't want to approach the thermodynamic limit because your unharmonicity of the ladder disappears.
So yes,
So that's what I'm kind of like asking that I mean, how we are kind of making sure that this is kind of individual molecules and not the ensemble effect.
so okay, you can be pretty clear this is not an ensemble effect because ensemble in the sense of having like 10 emitters on
Sure.
resonance. Now, how to tell that this isn't 2 emitters on resonance? The best that we were able to do with the equipment that we had on the day that we measured this was to look at it on like a single photon detected camera, and then just say like when it lights up, because you can see the width of the cavity on the camera. You know, it's about 10 microns wide, which is enough that you can resolve 20 pixels along that length. And is it just one pixel that lights up, or is it 2 pixels that light up at the same time, indicating that there's like a distributed effect? Now, is that perfectly rigorous? No, probably not.
How would you do it more rigorously?
Well, as Hossein said, you could do a G2 measurement and just see. Although it's, I guess even there it's a little tricky because let's say it's 2 molecules, right? Your G2 floor is not going to be 0, but it's also not going to be a half.
No, yeah, I think that if you do like a density dependent measurement, then you see that the floor of your G2 raises till you get like 1, right?
So,
because your ladder becomes harmonic. So if you have like ensemble, because the blockade effect, which you are kind of like alluded into, that leads to that single photon emission, it really based on the kind of like saturation of your single emitter, with a single photon. So now if you have like ensemble, then it becomes like bosonized limit, so then you don't see that saturation, so your ladder becomes harmonic. So that's why you're losing the advantage.
Yeah.
So if you do kind of systematic measurement as a function of density for G2, I imagine that your floor is kind of like raising till you get like 1.
Yeah, it would be very difficult to do that kind of density dependent, because like I said, so as I'll show later, we also pump this with a laser light, see all the molecules move around. And that kind of reveals like, if 2 molecules cross over, then you see that the dip gets much deeper. But generally it's very unlikely for 2 molecules to have the exact same resonance and then also to tune at the same rate. And if it's, but you're right, as you go into the ensemble limit, the floor of the G2 would raise. So.
I have a question. So how many molecules are in this crystal?
The entire crystal?
Well, that's in the cavity part of the crystal.
So it's going to be about 100 molecules per square micron, looking from the top. The cavity is going to be like, cavity mode is like 4 microns by half a micron. So that's in principle, 200 that are within.
Why don't I see 200 here?
For the same reason that the cooperativity is only a half. Okay, I'll just explain it. We suspect, so this is what we were expecting to see. We're expecting, if you do the simulations, you should get a Purcell factor of about 100. We're getting a Purcell factor of 2.5. What that probably means is just that the anthracene is not touching the cavity. It probably just means there's a little air gap here. And there are a lot of reasons for that. The most likely is just that you have like a chunk of something here and anthracene can't quite touch it. It's close enough to couple. It's close enough for like 10 to couple, but it's not quite touching it. But then also to your point, why don't you see 200? There's also the fact that, it's 200 molecules, but they're spread out over an inhomogeneous broadening, and the cavity overlaps with a portion of that. So,
Oh, got it.
so they're counted as two effects working.
Okay.
Yeah.
But that in homogeneous broadening, you said was 90 gigahertz. Is the
It's about twice this is the
okay.
inhomogeneous broadening. But you could be looking at it like perfectly overlapped, or you could be like here, and you're just measuring the tail end of inhomogeneous broadening. So, yeah.
And then the next slide on the reduced. Oh no, the one with the simulation on the reduced coupling. Yes.
Yes.
So this G is this 10 gamma is assuming the distance.
This is just a simulation. This is the same cooperativity that we have. This is a cooperativity we're expecting. Maybe get strong coupling in the future.
Okay,
That's
got it.
is the idea of it. But yeah, the yeah.
Do you know because you had this picture of that there was maybe a gap between the crystal and the cavity? How large would that
It'd be at least 100 nanometers, possibly more. So just doing some just a few simulations, like 100 to 200 nanometers maybe, which is large enough that it could be a particle of dust. There could be other effects, like we have seen with some of the scaffolds that we build for the crystal to sit on top of, because the crystal's flat on the substrate here, and then it bends up to go over the silicon nitride cavities and bends back down. And so maybe it has like this bridging effect where when you cool it down enough, it pops off. That would be unfortunate, but we're going to take care of that in the next generation of these devices. Just like put some supports here and there, and then make a whole bunch of different ways of scaffolding the crystal, and then just do atomic force microscopy over each of them and see which one is the most flat. Or it could just be a matter of being obsessive about the cleanliness to make sure there's nothing there that can sit on top of.
How much do you expect the cavity resonance to shift when you put the anthracene on top?
We expect it to shift about 10 terahertz or more, and that's another. Thank you for bringing it up. That's another giveaway that something's not quite right with this picture, because this cavity was designed to be at 780, and it's still at 780 after you put the crystal on. Whereas in reality, it should be at 800.
Yeah, that's not good.
So, in fact, the fact that there's coupling is a
It's an index of 1.8, so it should be a huge shift.
yeah.
Yeah.
So
There
you go. We're working on it.
Mhm.
Okay, so you can characterize the molecules as follows. Like I said, you can do this laser-induced shifting mechanism. You just put a lot of light into the cavity, and the molecules will undergo this permanent shift. And so you can tune them off the cavity, and as they go off resonance, the line shape will change, and the also the Purcell factor will change. So here's the lifetime on resonance, and here's a lifetime about kappa over 2 away from resonance. It's about decreased by about a factor 2, and so from that you can back out the Purcell factor. The beta factor 44%, which just means that if you were to excite the molecule from the top, then 44% of the light would go into the cavity. And that's compared to if there were no cavity, it would be about 3%. So even in this case where it's not touching the cavity, there's already a quite a large enhancement of the beta factor. But yes, of course, we are working on improving this, and it is nice that there is so much room for improvement, because in principle it shouldn't be too difficult to get to the regime where your beta factor is 99%.
And now you must be about break even with how much goes straight back down and how much goes through that vibration. It must
Yes,
be about 50-50. Roughly.
yes, yeah,
Okay.
yeah, that's right. Good. Okay. Now, of course, the end goal, as I mentioned a few times, or one of the end goals, is to make these collective systems, cavity-mediated collective systems, so you can get to the 10 molecule limit or the 20 molecule limit. And so just as a proof of principle, but of course not the ultimate result, is we just use the fact that each of these molecules, when you're tuning them, they all move at their own rates, and every once in a while they cross over, and then you can see the cooperativity increases. the soup or the enhanced decay rate and the subradiant state in these is a little bit different, in a sense where the symmetric state will decay at a rate of gamma prime, which is into the free space, plus, I didn't write here, gamma prime plus 2 gamma 1d, whereas the other one will just decay at gamma prime. So all that to say that you can use these collective interactions to enhance the decay rate of Niagara ensemble into the cavity, but you still can't suppress the decay rate into free space. That is not possible with the cavity, or at least not this geometry of cavity. So, okay, so that's where my PhD ends. We're still looking forward to the dream of being able to couple many molecules to a cavity, and then instead of using this random tuning mechanism, to use electrodes to tune individual molecules to have this site selectivity. And because these crystals are 30 to 50 microns large, you can make a 30 to 50 micron large cavity if you made it like a Fabry-Perot cavity. And then you could have, say, 30 to 50 molecules or maybe more that are all tuned into resonance. And what is cool is that these molecules, if there's no enhancement, they decay at a rate of about 4 to 5 nanoseconds, whereas the limit of how fast you can change an electric field is going to be something like 100 picoseconds. That's just a 10 gigahertz like electronic limit. And so you could imagine being able to shuffle things around even as the molecules are decaying, or perhaps before they've decayed. And then maybe in the atom world, there are all sorts of protocols of useful things you can do with that. Now, of course, we don't have a ground state here, a long-lived ground state, so some of those protocols won't apply, but maybe you can make some interesting kind of quantum light from that. All right, so I'd like to thank you all for your attention. I'd like to thank my lab for all their help over the years. This is David. He's our graduated. I told him I'd put him in the picture somewhere. And of course, an infinite amount of gratitude towards my family, my wife, who is also getting a PhD, for all her help taking care of our newborn daughter while I try to finish this up. So thank you.